as Jenny said, I'm going to be talking about parameter estimation, in particular the computational side of it for ground-based gravitational wave detectors. So if I just start going, hopefully you can see the contents now. Yeah, so briefly mention what parameter estimation is for advanced LIGO, Virgo, and CAGRA. Before rapidly moving on to what you're probably all more interested in is the computational challenges of that particular activity. And I'll say a little bit about some of the new approaches that have been developed by my group at Glasgow, along with other people as well across the world, to meet some of the upcoming challenges of doing this. And then most of the rest of the talk will be an advertisement for some recent work that we've been doing on nested sampling here that can have great potential to speed things up. So what, first of all, just in case there's anyone in the audience who somehow doesn't know what parameter estimation is, I can sort of show you in this one slide, which I've been waiting for over a year to be able to put together. The results from the third gravitational wave, the third observing run of Advanced LIGO, Advanced Virgo. What you're looking at here is 74 compact binary coalescences. Each of them has their gravitational wave code word, of course, and the violin plots associated with the parameter estimates from each of these events. You can see that there's a huge range of physics represented in this one plot, or in these two plots, I should say, from the two papers. But I'm not going to talk about that today. That's all really interesting science, but it's not of the computational aspect that we're going to focus on the rest of this talk. But I will plug to the webinar that's happening on Monday, where you can hear a lot of the interesting science about this that's being presented by the team behind GWTC3. So if you want to know more and I can't satisfy your curiosity, then do register at that link that's on the screen right now. But what you're basically seeing in these plots is Bayesian probability represented by the thickness of the blob and distributed over the particular parameter, which is on the x-axis in each of them. So you've got your masses and spins, luminosity distance on the left, and on the right-hand side, we've got chirp mass, spins, and luminosity distance. So maybe not entirely consistent the way I've shown it here, but that's what you're looking at. So in order to actually get these results, which tell us what it is that we're looking at when we see these detections, we have to run computational algorithms, Bayesian inference methods, and we'll be looking at how they work for the rest of this talk. But I shouldn't really proceed to that before I say a little bit more, because we're counting computational costs. So you need to know what it is that you're buying and how many of them you're buying. So in these two most recent catalogs were 74 events. And that brings us a total of 90 with p-Astro greater than 0.5 that have been detected by the LVK and by outside collaborators as well in the data since the start of the observing run, the first observing run in 2015. And you might think, well, that's amazing. Look at this plot that shows you the rapid growth in the number of detections, that we're almost 100 events now after just 3 observing runs. And the huge amount of work that's gone into getting those results that I showed in the last plot shouldn't be underestimated. But you can see, I think, visually the scale of the problem moving forward. If I just visually represent the size of 04 compared to 01, 02, and 03 on the same plot, that'll take us up to something like 220 odd detections if you just do a straightforward projection, assuming the kind of median sensitivity curve for 04, that's the current prediction. And then becoming even more speculative, but going on to 05, design sensitivity and beyond, you're looking at something like this every year. Now, this plot is highly unfair because, of course, it's a 2-dimensional square, but it's really a 1-dimensional quantity. So the visual impact of this plot is rather greater than the actual impact of the number of detections. But nonetheless, I think you get the point that what we've been dealing with up to now is kind of something like 1/20th of what we will be seeing per year in '05. So there's definitely a challenge coming our way, and it'll be here before we know it, given the rate at which things are moving, to actually deliver all the science that I've been showing you in the first slide. So hopefully that will motivate everyone to pay attention because they want to know how we can do this. But let me go back to the boring computational details about what we actually did in '03. So I won't put the specific cost on this slide because it's alarming, but it was tens of millions of CPU hours that we spent doing these parameter estimation runs. That's not including the time that it took to do development of the codes and simulations and preparation to do science modeling and so on. And it also doesn't include the cost of doing all the testing GR, which is largely done with very similar types of codes that treat deviations from general relativity as just a sort of parameterized deviation. So you can kind of double that vague tens of millions if you want to get the total cost of running these codes over the course of '03. Part of that number is so high because we did do quite a lot of duplication. There were 3 main pipelines used, and we do cross comparisons internally to give us sort of confidence in the results and consistency. The 3 main pipelines that have been used in '03 are LAL inference, of which I'm one of the primary developers, which is kind of giving way to Bilby, which is a more Python-based code. And they both work in largely the same way with stochastic sampling algorithms, namely nested sampling and Markov chain Monte Carlo. And the other big one is Rift, which is also known as Wrapup. And that uses a combination of Monte Carlo for extrinsic parameters and a grid for intrinsic parameters like the masses and spins. So those are kind of our big workhorse codes. And as I say, we use similar codes, in some cases the same codes with extensions for doing testing GR. So the applicability of these particular codes is quite broad within the collaboration. They're used a lot and they account for a large fraction of the computing resources that were used in '03. Interestingly, when I looked at the numbers, I was surprised to learn that we actually spent less computing in '03 in the production runs than we did in '02. So we're doing something right in terms of scaling. We can handle the amount of events that we've seen in '03. And I'll talk a little bit about what actually happened at the end of my talk to make that possible, because it wasn't actually necessarily computing that made that possible. I think my theory from this thing is that computing costs will expand to fill the available resources no matter what you have to do. So I'm going to drill into some of the details for the next part of this talk. I'm going to talk about computational scaling to give you an idea of why these things are so expensive and how do they scale with regard to the most interesting physics. And the reason that we need to do that is so that, well, so we can understand what it is that we're doing, but also identify where there's room for improvement. Bottlenecks in the code, serializations when they should be done in parallel, and things that are inefficient when they could be made more efficient with the application of some intelligence and some innovation. I'm most familiar with nested sampling. That's kind of been my main project when I was working in parameter estimation all the time. So I'm going to use that as our kind of algorithm we put under the microscope. So there might be people in the audience who never really looked into nested sampling before, and I'll try and explain it to you in one slide. It works on a loop, and I've got the loop on the left-hand side of the plot. And on the right-hand side, I have the schematic, which gives you the understanding of what it is that it's doing. So unfortunately, my cursor doesn't seem to appear very well. But in the upper panel of the plot, there is the contours that represent these Bayesian probability distributions in parameter space. And if you imagine these are kind of, well, they're like levels on a topographical map. So the inner contours represent higher likelihoods than the outer contours. And what nested sampling does is it takes those low likelihoods and high likelihoods, and it makes the observation that all the points of a high likelihood lie inside a contour with a lower likelihood. So if you work your way in from the outside, then you can estimate, this is the really clever bit, it's not so much the algorithm itself, how does it estimate the volume of these contours in high dimensional spaces? That's the clever bit. It does that by statistical estimation using a set of live points. So on the lower panel of the plot, you can see the same contours on the left, and on the right-hand side now we have these live points. So at the bottom, you read this from bottom to top. You start with samples that are distributed completely at random within the entire prior volume, and you pick out the one that has the lowest likelihood, and you say, well, what is the volume contained within that likelihood contour? And you can get a statistical estimate of that, which is roughly equal to n minus 1 divided by n, where n is the number of live points. In this case, it's 3 on the plot. In practice, it's a lot more than 3. So that gives you an estimate of what the volume of that first contour is relative to the whole prior, and then you replace that bad point with a new point that's at a higher likelihood. And you keep on doing that, you work your way in, removing a point at each stage, and you use the same statistical trick to estimate the shrinkage of the contours at each step. So what you end up with is a geometric progression to smaller and smaller volumes and higher likelihood. And eventually, the determination condition that basically lets you work out how much of this probability is left within the current contour. Once that becomes sufficiently small, then you stop the algorithm and you're done. So it's a really nice method because it's kind of guaranteed to finish, which is one of the big problems with MCMC, is that you kind of have to judge when to stop it. Nested sampling always has a termination point, and once it's done, it's done. And it will always reach the peak of the probability distribution because of this geometric shrinkage, that no matter how small the mode is, given that you have sufficiently high number of live points that you're not going to miss it, then you will always get a good estimate of the evidence and establishment of the theory. Okay, so I should be animating these as I go along. So that is my one slide description of how nested sampling works, and I'll show you in a different way with an actual movie that shows how it works for gravitational wave inference. So here's some two-dimensional projections of parameters during a nested sampling run. You can see it's scanning, starting off with the red points being the live points and the blue points being the dead point. It's initially filling the whole space, and as it goes up in likelihood, it starts to narrow in on the correct sky location and the correct masses. And eventually, at the later stages of the run, you see different parameters freezing out at different times. So it's kind of interesting, actually, because once you get a feel for this method, it shows you where all the information is in the data. And by information, I do specifically mean information that, as in something like the entropy or the negative entropy, the log of the ratio of the posterior volume to the prior volume. And you can quantify that with nested sampling as another advantage of the algorithm. So starting to think about scaling, the number of points that it takes, the number of iterations of this algorithm that have to happen before it stops, is actually, you can estimate it as the information content measured in nats, or if you like, times number of live points. So that's our first piece of scaling. Now, that's all well and good, so you don't really know how much information is in a particular piece of data. But for something like a binary black hole that's detected, in a second generation instrument, there'll be something like 30 naps of information in the data. More at higher SNR. Higher SNR gives you more information, of course. And also longer signals give you more information. So because the stereo is much narrower for a binary neutron star than it is for a binary black hole, that means that the probability is much more concentrated, and that means that the information H is a higher number. So you can compare that 30 for a binary black hole to maybe 40 for a binary neutron star. So if H is 30 or 40, then all you need to know is what n live is, and you'll get some idea of the number of iterations you have to run this. You can see in my animation that it's going to around about 30,000 iterations. So the number of live points that I use to make these movies is about 1,000. In fact, I think it's exactly 1,000. So there you go. You have to run it for 32,000 iterations in this movie to solve the problem. All well and good. Now, what's the first issue with this? Well, the first issue with this is that it's a loop and inherently not parallelizable. So that's really the biggest problem with nested sampling, as far as I'm concerned, in that the naive version of the algorithm, you have to do it iteratively. So, for example, lull inference nest, which is my kind of pet code, it runs on a single core, just because it was written back in the day in a C code. I didn't want to deal with multi-threading, so that's what it does. But you can run, thousands of them at a time and merge them together, so it's all right. Okay, so the other big problem with this is this middle box, which hides a lot of horrible details. So how do you pick that new point that's inside the current contour? That is really the biggest challenge in nested sampling, and all the different flavors of nested sampling that you can get do that in a different way, or in one way out of a few different possibilities. But all of them, I think you can describe. Sorry, all of them you can describe with this little box that I put together. You got to draw a trial point that you think is good. You always have to check that it has a likelihood higher than the limit, otherwise you can't accept it. Now, after that, you have to decide, is this point statistically independent from my last point? So if you're drawing this new point using a small Markov chain, then you might want to run it for a certain number of steps before you actually accept the point, because you know that the Markov chain always has some finite autocorrelation length. So there's two variables there. One of them is the efficiency at which you can pick points that have a likelihood greater than the previous one. And the second one is the number of steps that you need to run for before you get a statistically independent point. So I've got autocorrelation length and the proposal efficiency as the next two factors in my analysis here. But even this is hiding quite a lot of detail, and actually we've not even got to the nasty part yet. So we can move on to the third box in this well-proportioned diagram, and that is computing likelihood. So this is actually where all of the cost comes in, because this is the hot loop. This is what you have to do over and over and over again. And in order to do that, first of all, you compute a waveform. Then you FFT it to get in the frequency domain if it's not already in the frequency domain. And for gravitational wave, ground-based problems, you've got a network of detectors. You shift the waveform to the appropriate time for that detector. You project it on with the detector response functions. And finally, you compute the inner product of the residuals to give you the likelihood function. So I'm not going to go into the mathematical details too much, but all you need to know is that this consists of multiple stages. And these different things all have a cost, and because they are the hot loop, they are the main things that you have to look at optimizing if you want your code to run fast. So when you're running parameter estimation, you're computing waveforms over and over and over again, basically. So what the cost of each of those waveforms is something proportional to the length of that waveform times the sampling frequency times the number of detectors. So well, maybe that last times the number of detectors is not fair because there are tricks you can use to project them on quickly. But you can't really get away from this number of data points scaling. If you have 10,000 data points that your waveform is defined on, you're going to end up doing at least 10,000 floating point operations in order to generate that waveform. The tricks that we're going to come to all involve reducing those number of data points, basically. Okay, so just to give you an idea of what we're talking about, I ran some benchmarks yesterday for some of the more popular waveforms. So this is all on my home computer. Oh, I forgot to fill in the binary neutron star with the ROM. Sorry, I left it running overnight because it was taking quite a long time to run SAB and RV4PHM on a binary neutron star. As many of you can imagine if you've ever tried to do that. So at the top, we've got IMR phenomena, phenomenological waveforms. These are based on basically splines or polynomials in frequency to give you the phase and amplitude. And inside the code, it wraps those up based on the align spin, and then it twists them around if there's precession using a prescription of how the orbital plane precesses. So it's there's a lot of intelligence that goes into them, a lot of physics heuristics, I would say, that go into those, and the result is that they're very fast. It takes about a millisecond to generate this BBH waveform that I picked out a hat, and it only takes not that much longer to generate a binary neutron star waveform. So a very long binary neutron star waveform, 196 seconds, starting at 20 hertz using a sampling frequency of 4 kilohertz. It still takes less than a second to do that on my desktop computer, which is like 3 years old. Similarly for Phenom XPHM, that's giving you similar results. The real big one are the SUB family. So SUB and RV4PHM, I should probably explain what these cryptic letters mean. So IMR is spiral measure ring down, phenom means phenomenological, P means precession, and HM means higher modes. And the X, I believe, stands for mystery, as it always does. So SUBNRV4PHM is the spinning effective one-body numerical relativity version 4 processing higher mode waveform. So that is really the absolute creme de la creme of waveforms, if you ask me. It has all the physics in it. It has higher modes, it has precession. It's all based on physical prescriptions and partial differential equations that you have to solve in the time domain in order to get the waveform. And it's got the biggest range of numerical relativity it's calibrated against. So, if you want to generate one waveform, use this waveform family, is my advice. But you'd be prepared to wait a little with time to do it, because it took me about 5 seconds to generate the VBH waveform with this particular waveform family. So that's just not practical. We have to generate 10 million waveforms to solve the parameter estimation problem for VBH in O3. So instead, what people do is use the first of the tricks that I'm going to talk about, which is reduced order modeling. So I'll just move on to my next slide. So reduced order modeling is simple to understand. So you take your waveform, you generate a whole lot of them and unwrap them into an amplitude and phase part, and fit each of those with, or decompose them into basis functions and use a spline to interpolate the weights on those basis functions across the mass ratio and the spin space. So this was introduced, first of all, by Michael Purer in this 1512 paper, and recent paper from Roberto Testa on the more up-to-date versions of these. I highly recommend you have a look at this if you don't understand, if you want to dip your toe into these tricks. So this is really good because it means that you're no longer solving PDEs. and for SEOB, it's kind of essential to do that in order to make use of it in any kind of serial type code. And another thing is that it's also lends itself quite well to implementation on a GPU. And so people have recently been porting some of these reduced order model type codes onto GPUs. So it's giving you about 1,000 times speed up for these very slow waveforms and bringing them into the realms of usability, I would say. The next trick is commonly confused with reduced order models. It's called reduced order quadrature. And depending on who you ask, those two things might mean the same or not. But I always refer to ROQ when I'm talking about taking that inner product that's formed in the frequency domain by summing over frequency bins and replacing it with a different basis. So instead of using the Fourier basis, you work out a basis that's tailored to the particular problem. And you can re-express that integral instead of being over the frequency domain, you express it over the new basis. And that's even faster than reduced order models, because for reduced order models, you're accelerating the waveform. Reduced order quadrature, you're accelerating the entire likelihood function. You don't have to do the sum over frequency bins at all anymore. But that means that you have to do some pre-computation to get the coefficients for the ROQ basis to begin with. And that's challenging. Either you have to do it for a little slice of parameter space, or you end up with a gigantic matrix to solve for if you try and do it for a large prior. And you need something like, several terabytes of memory to build the basis in the first place. So it has its drawback, but it is very fast. Multi-banding is another idea that people have tried out, including my student Serena Vinciguerra, more recently Soichiro Murasaki. That gives you kind of a 50 times speed up for DNS. It's kind of the simplest thing you can do. You can look at the waveform, it increases in frequency as a function of time. So you don't need to sample it at a uniform frequency for all time. Instead, you can just fit an envelope and keep it below the Nyquist rate at all times. You get a speed up that way. It's not as big as the speed up you get from ROQ, but it is easier to use. So you don't need any pre-computation. So you can kind of drop it in as a replacement. Unfortunately, it's not terribly well supported by a lot of simulation. So it's not really caught on a lot, I would say. What has caught on more is this heterodynamic likelihood, also known as relative binning. That was first introduced by Neil Cornish back in 2010 and has been kind of reinvented by Zakai. And Daniel Finstad also looked at it recently with PyCBC inference, showing very impressive speedups there. And the general idea is that you don't compute the entire waveform, all frequencies. You just take a reference waveform and compute the difference between that reference waveform and the proposed waveform. And the bandwidth of that difference is much less than the full bandwidth of the signal. So the number of data points that you have to use is much less than you would do in the full signal. So remember, I'm saying that all of these techniques are just reducing the number of data points that you have to compute, or the number of iterations that you have to solve a PDE in the case of the first one, I suppose. So that gives you a speed up similar to ROQ. It's kind of like ROQ in a way, if you think about it. The nice thing about it is it doesn't require any pre-computation other than the generation of the initial reference waveform. So it's very powerful for things like binary neutron stars. But it's not so applicable to these time domain-based waveforms where you have to solve a PDE. That usually works by taking steps. And so if your entire idea is to reduce the number of steps you take, but that number is less than the number that is required to solve the PDE, then you can't get any benefit of it. You still have to take all the steps to solve the PDE. So this is all really clever stuff. All of these methods can be used and have been used to solve the parameter estimation problem for compact binaries. But they're all looking at just one part of the total computational cost. So what I actually want to talk about is this part in the middle for the most of the rest of the talk. I've only got 10 minutes left, so I'm going to run through this quite quickly. I've used a lot of my time up already. Because some of the work that we've been doing at Glasgow is more looking in this area, which is maybe receiving less attention than the waveforms and likelihood, but is in the middle of this computational cost calculation, still rather important. So yeah, looking at this autocorrelation length times epsilon. So how do people currently generate these new points for nested sampling? Well, there's a few ways. There's random walk, where you're doing a little MCMC, and that is kind of the dumbest thing you can do. But also it works quite well because you have all the other life points to look at to judge the size of the step that you need to take and the direction that you need to take it in. So it's quite robust, and you can do a bunch of tricks to tune it automatically, which we're using law inference, for example. But the autocorrelation length of those MCMT chains is still rather long. So it's something like 5,000. I never run law inference with a maximum chain length less than 5,000. So if somebody's saying that they did it with 1,000, I would raise my eyebrows about the results, to be honest. So that's a problem because that means that you're automatically taking 5,000 more iterations than you really need to in the best case scenario. Slice sampling is another one. It's a bit like Gibbs sampling. That has advantages in that it also can set its own scale, but it has similar disadvantages that it has long autocorrelation lengths, and it doesn't handle multiple modes all that well in some cases. And the other big one that's used is bounding boxes or bounding ellipsoids. So that's multi-nest trick, and it's also used in Nessel and Dynasty. The big advantage of that one has, I say, zero ACL. It should really be one ACL because each point that you generate is physically independent from the last one. But the problem with this method is that if your bounding box or your bounding ellipsoid doesn't have the same shape as the contour that you want to draw within, which is the case in this diagram here, then you have an inefficiency because you're going to end up drawing points outside of the contour. So you might look at this in 2 dimensions and say, well, that's no big deal. I'm going to get an efficiency of about 50% in this shape. But as you go to higher and higher dimensions of the problem, the volume inside a given box, it moves to the outside of the box. So basically all of your samples that you draw will be at the edges where you're most likely to miss the contour that you're trying. So at the end of the day, when we were doing this with multi-nest back in the day, we found that actually in order to get good results, you had to make that box so big that you had to draw about 5,000 samples before you got a hit. And so the efficiency that you get from having an autocorrelation length of 1 is kind of killed by the poor sampling efficiency in the dimensions of a compact binary problem. So, it's a bit of a trade-off in either direction. So I was always wanted to try and solve this problem, and I had a very good student come along called Michael Williams, who's been working on this for the last year or so. And he's put together a code called Nessie with a Scottish flavour, but spelt with an AI to give you that little taste of machine learning, because that is the magic ingredient in this method. So I'm going to explain how it works, and then I'll wrap up with a little advert. So these contours that we're trying to draw things within, you might not be able to learn them with ellipsoids or something like that, but you can try and train a machine learning algorithm to approximate them. Now, the method that we're using is called normalizing flows. And basically what it is, I'm going to explain what it means. The normalizing doesn't refer to the normalization. It means it tries to take a blob and make it look like a normal distribution. So it's taking this banana in the parameter space and trying to squash it down into a nice circular distribution that's very easy to sample from. So if you can draw samples from a multivariate normal distribution, or even just a product of univariate normal distributions, then you can apply the inverse of the flow to get your samples back in the physical parameter space. So I will skip over this diagram that shows you the traditional layers of the machine learning machine. If you want to look at the details of normalizing flows, you can look at the paper referenced here. And if you want to see how we do it in particular, you can look at the reference for Nessie that I will put up again. So yeah, we start off by drawing a contour. We want to draw a contour that contains all of those. So what we do is we apply the normalizing flow, transforms from X space to the Z space. The flow itself can be trained on the live points because we've got all of those points hanging around nest sampling, of course. And then in the latent space, we call it the Z space, that distribution is Gaussian, so we can easily sample it. So we draw new samples inside the Gaussian and apply the inverse of the map to get them back into the physical parameter space X. But those samples are not, unfortunately, distributed according to the prior in X. So there's an additional step of rejection sampling that needs to be done before we can actually use them. And once you've done that last step, then you have nice uniformly distributed in the prior samples inside a contour that you can feed into the standard nested sampling algorithm. And they're all statistically independent, which is great. So this tells you the efficiency. The autocorrelation length is 1 because they're all independent. And the efficiency should be pretty good because we're using machine learning to learn the shape of these contours, essentially. Unfortunately, there's a rejection sampling step that we have to deal with. Oops, got my build order wrong. Okay, so I should say that this is not a complete silver bullet. There are problems with some of the parameters that we need to solve for because of the type of flow that we're using. So one of the things that we're working on is looking at different types of normalizing flows to improve how this works for our gravitational wave problem. But nonetheless, it works really well. Here's a PP plots, which you have to show if you want anyone to take you seriously. So this tells you what fraction of the time we get the Bayesian variable interval correct. And if you're doing well, then all of your curves should be inside the gray area. So yeah, basically this is showing that we do solve EP plots correctly. So that's all well and good. It's a nice idea. But if it's not actually faster than current methods, then it doesn't gain us very much. So we did the comparison with Dynasty, which is kind of the workhorse for Bilby and for PyCPC inference as well. And if you look at the number of likelihood evaluations, then you see, well, okay, I should explain this plot a little bit better. Dynasty took on average, or sorry, median of about 10 million iterations to solve BBHs. We can do it in 3 million. So factor of 3 speed up in the number of likelihood evaluations translates directly to a factor of 3 speed up in the runtime of the code. In fact, slightly larger in some cases. So that's bringing you from around about 1 day or just over a day down to less than a day in all cases, or in almost all cases, for binary black holes. This is using kind of none of these waveform speed up tricks, by the way. This is kind of doing it in the hard way. Okay, all well and good. And of course, I have to show you one of these corner plots just to prove that the contours look right. So you can come back and look at this later if you want, but the contours do look right. I wouldn't allow you to see it if they didn't look right. Another nice thing about this method is that because you're drawing all these points from this latent space Gaussian at once, you can parallelize that very nicely. So this scales much better than previous nested sampling methods. show that it scales almost linearly in the number of threads that you can throw at it. Unfortunately, there's a bit of an overhead left because of the rejection sampling and the training of the machine learning. But basically, if you throw enough cores at a problem, you can solve it in something like 3 hours. In fact, if you, well, in this case, it's 3 hours for the problems in the paper. This is a more recent one. If you're using this algorithm, which hopefully I'm going to convince you to do, then you will get one of these plots spit out after every run as a diagnostic. So one of the things with these methods is that you can kind of never know when to trust them. I see Jenny standing up. Does that mean I should wrap up? She's nodding. Okay, I'll get to the questions. Okay, I'll explain this later if anyone wants to know, but trust me, it's showing that you can actually get some insight into how well things are going. You can see the efficiency is hovering around a nice value, so it's all performing very well. Okay, so I will show you this advert, so you can just jot down the name of the code again if you want to use it, and finish up by asking, what are the ultimate speed limits for gravitational wave parameter estimation? So I put down here that waveform kind of costs a few milliseconds. If the proposal is perfect in autocorrelation length times efficiency is just 1, then you can kind of factor that out. But there's this issue on the left about the number of live points and the information content in the data. So that's kind of where we're looking to go next, is parallelizing the outer layer of the algorithm a bit more so that we can spread things out even faster. So I'm assuming that everybody else has solved the waveform problem, and we're working on the proposal on the main algorithm of message sampling itself. So I think that we can solve full parameter estimation problems for generic signals within minutes if we just take the existing technology and evolve it, even without requiring any of these waveform acceleration techniques, which are great. Okay, so I'll wrap up now. I'm just this is my slide that has all the references to all the other things you could be doing. In particular, though, I'll point out that you should listen to John Gerst's talk, because he's going to talk about likelihood-free inference, which is, I think, the big, biggest development in recent years about getting to ultra-low latency. So that's going to be really promising. But we're kind of filled a flexible niche. We don't have to pre-train anything. Just drop it in instead of using MC. Okay, so I'll wrap up saying all of that is great, but the costs don't add up to what we actually use in terms of CPU hours. The problem is not actually computational, I think, or it hasn't been so much, especially in the early days. We do a lot of exploratory runs. We repeat things. We do trial and error until we get the settings right. We have to do things multiple times to check that we've cleaned the data and not influencing the results. And then we do it all over again with everything finalized, just to get it right with multiple waveforms and samples and different priors and so on. So there's a lot of redundancy in the parameter estimation that we're doing at the moment that is not a computational problem, but we can still use computing to try and help us solve that. So the other thing that we've been working on at Glasgow recently is this Asimov robot, which has been used to kind of standardize all of this in O3B and a little bit in O3A as well. So that has been part of the reason that we were able to do more using fewer resources without sacrificing the quality of our results for O3. So a little plug to Daniel Williams for working on that. Okay, so I'll wrap up there. I think hopefully you've been interested. I've explained to you how these algorithms work, and I'll just finish there. If you have any questions to ask me, I'd be happy to talk more. Looking even further ahead, though, I think the third generation is not going to be solvable with these existing techniques evolved, because the problems scale even worse with the length of the signals and so on. So there's still some innovation required in terms of algorithms, and I think machine learning is providing a lot of that impetus at the moment, but there's lots of ways that you can use that. And so we're going to explore all the different possibilities. It's an interesting time to be working on this field. All right, thank you for listening, and I'll be happy to take questions.